Welcome everyone to the first DataBeers Brussels.
Yay!
Good evening, everyone, to the 19th edition of DataBeers. Can you hear me well? Yes?
Yes.
Okay, great. So I promised I would be very tired and completely a bit messed up because I took exams all day and I'm drinking Orval, so toxic combination. And I'm wearing a t-shirt of Politecnico. If you're a fan of Belgium, you should visit Police Dogs during the 21st of July. Anyway, off topic. So what's DataBeers? So DataBeers started in Madrid a long time ago. Well, a long time ago, 10 years more or less. And so there are many chapters around the world. So if you ever move, there is no excuse because you can either find an existing chapter or start your own across the world. So what's DataBeers? It's a place, it's an event for people who enjoy data and or beers. So the concept in the physical world pre-COVID is we have some beers to warm up. There are interesting talks, not too long, no formulas, no code, no advertisement, and afterwards we have even more beers at the local bar. Of course, now we're in COVID times, so how does it work this time? So if you want to chat, you have something to share, please do by using the chat function in Zoom. If you want to ask a question, please do in the Q&A section. And so don't put your questions in the chat section, but put them in the Q&A. And if you want to ask a question by voice, in the natural way, you can raise your hand, and our great master of ceremony, Charlotte, will make sure that you will be heard. Voila. So please, we're a small crowd. It's meant to be interactive and fun, so don't hesitate to ask questions. Voila. Also, it's DataBeers, so we expect you to have a beer. So this is the time to pour yourself a nice beer. Voila. So who is DataBeers Brussels? So we've been growing. So founders is really Jelena, who is really the driving force. If we could reproduce energy, like renewable energy, like Jelena would be like nuclear power in square. So she's really the driving force, and we're very handsome sheep, helping her, supporting in our efforts to make this happen, which is, I think...
Yeah, I couldn't do it alone. Without you guys, I don't think it would be possible. Yes,
but anyway, I think we do a great job attracting really nice speakers. So we're there's a whole team behind this doing PR, attracting speakers, organizing the events, and so on. So now, who are you? So if you like, please answer our poll in Zoom. So, oops, I'm a bit too fast. What's your background? So where are you from? Are you from academia or industry? And then we can have a look at the results. So I see, and that's the fun part about this DataBeers, that it's always very balanced with people from industry and academia, which is really nice to see that there is some, so it's a good place to connect. And then you needed some people like us, we needed just an excuse to open a beer, of course. But it would be really nice if you could share in the chat a bit more about yourself, so you get to know the others, like what's your favorite beer? There at the left, you can see my favorite beer, where you're from, and your favorite composer, because we have some talks about music in this session. And so at the top right, you see Michael Jackson, if he were still alive, but he's not, unfortunately. Sorry, apologies, by the way, for my way of introducing DataBeers. I can't help it. It's I do it my own way. But so please drop a message in the chat where you're from, what your favorite beer is, what kind of music you like. Let me do it myself. I see quite some lovers of Chopin. That's nice to see. No, Yelela, you're cheating. You posted twice. Anyway,
Once was the only panelist, so that I have to request everybody can see.
Okay. So, who do we have today? So we have 3 speakers for today: Samir Salim, Isabella Douzoglou, and Sebastian Gonzalez. Apologies if I don't pronounce the names very well. There's a nice thing about online events that we can go abroad and invite speakers around the world, but they will be introduced in a minute. So don't worry if you want to know more. So data and beers. So the question is, do data drink beer? And honestly, so we have DataBeers is about stories about beer. And today I had very little inspiration. And I'm starting this movement of no data. So I wondered, do data drink beer? And then my computer corrected me, does data drink beer? And because he added the ES, I wondered, is it the San Miguel? Very interesting question. So computer says bad news, because data is some character from an intergalactic television series, and data doesn't drink beer, or I couldn't find any evidence of data drinking beer. But in Data Lore, an episode from Star Trek, Data discovers that his brother is immoral. And so he learns that he was created after Lore. And so my question to you is, did Data start drinking beer afterwards? So I want to hear your opinion about this. I can no longer see the results, unfortunately. But, oh, Yes, I think too. Let's be honest, probably Data started drinking beer afterwards. So that was the bad news, which turned into half good news. But the really good news is that actually Data is an actor. And so this is the actor that plays Data. And he looks like a guy I want to hang around with and have a beer. There's something strange about this guy that he spends more hours of the day in makeup than out of makeup. But yeah, who cares if you can have a good beer? And so to wrap up, I want to tell you a joke about Data. So it goes as follows. Someone asked Data, can I ask you a personal question? And Data says, yes. Are you PC compatible? Okay, that was a joke. I know it was not funny, but if you got a better Data story, I think it shouldn't be that hard. Please send us an email to DataBeers Brussels so we can invite you for one of our next events. Also, please, after this event, please answer our survey so we can improve the DataBeers events. I hope the next event we can have live again in Brussels. And by the way, we will send beers or drink beers with the people that ask the best questions during this event. Voila. Now I leave the floor to Charlotte.
To me, yes. Okay, so hello everyone. Thank you for coming to this event. So our first speaker will be Sebastian. So Sebastian, he's coming from Chile, and he has backgrounds in computational physics, right? And one really interesting thing about Sebastian is that while he was doing his PhD in the Netherlands in computational physics, he discovered another passion, which is actually violin making. And that was something that he really discovered and really liked. And several years later, when he went to the events of the Festival for the Violin Making and Instrument Making in general in Italy, he discovers that there was Acoustics Lab in the world famous museum of violin making, but also all of different like string instruments making. And he knocked at the door and said, please, do you have a post for me? I would really like to work in this kind of environments. Looks really fun and really cool. And he got it, right? And that's how he arrived to this story that he will tell us today about how can you use data to make violin or to improve the making of violin. So Sebastian, the floor is yours now.
Okay, thanks, Charlotte. Let me share my screen. And great. That's the shape the price violin. Perfect. Okay, people actually congas. Okay, good. So the first question is, you see my screen, no? Okay.
Yes.
Perfect. The first question is, I don't know, because perception and the tone of something, it's a subjective experience, which is determined by a lot of factors. So if you have something expensive, you're probably gonna think it sounds better. So I think that's a question science at the moment cannot answer. The other question is like, what instrument we don't play, the authors of the paper that I'm presenting now, it's actually violin. And as Charlotte said, I ended up doing violins just by chance. I met Julia, my first wife, and currently my ex-wife. in Holland 7 years ago. She took me to her family's house in Celle in the north of Germany, where I started to learn to love German beer. And I entered the workshop, and the smell, the woods, all this magic, I just fell in love with it. And I decided to start right there learning how to make instruments. And the question, like right there, was like, how can I use my knowledge as a physicist and my programming abilities to improve violin making? It's taken me 7 years to just starting to figure out what I'm going to do. So the first thing for me, it's the relationship between structural mechanics and shape. That's always something that always has fascinated me. And an example here in Italy, I have also the pizza and the espresso machine there. It's the arches, the Roman arches. And it's a very simple geometrical shape, half a circle, where the elements, in this case, the bricks or the stones, they can bear loads much bigger than their own weight due to their particular shape. And the way they created these shapes, it's from back in the days of the Romans till the Middle Ages and probably till Descartes, was just with ruler and compass. And people created everything from cathedrals to instruments with these two tools. And we can see here in the left a drawing of a violin, which is made just with circle pieces, arc of circumference. Different points and different angles create the shape of the violin, a shape which is rather complicated and organic, but that it can be defined by numbers. And we will go back to this in the future. Okay, so how do we train a network with violins? It's kind of tricky because we're used to, I don't know, the typical example, it's a cat and a dog and you have a picture, but the picture of a violin doesn't tell you the whole story. In this case, there are different pictures of different makers and a lot of Stradivarius. This is on the entrance of our lab, both in the visible on top and the UV on the bottom, which shows you things about of the varnish. But actually, the violin and even I have a guitar here. I left the violin in the office Monday. They are three-dimensional objects, so you need to take account of all the complexities of the arching. That's the curvature, both in longitudinal and transversal direction. In what are we interested in measuring? Okay, the sound is something very complicated that it's actually a 3D field in the space. We go for something much simpler, which is just the eigenfrequencies. For those of you who don't know, the eigenfrequencies are like the fundamental nodes of a structure. If you think of, for example, guitar string, they are sinusoidal movements. In the case of a plate, like the violin, it's a bit more complicated, but each shape has associated a number. That's the eigenfrequency. In this case, denoted by F1 to 5. So to create these artificial violins to train the data set, we use the drawing from the 1800, which is 16 points with 23 parameters, plus the thickness of the plate, because in violins are not homogeneous things, but they have different thickness on the top depending where they are. In the left, you can see an historical example. In the right, 3 of our artificial violins. And we took those parameters, put it in a really simple neural network, it's like a perceptron, and the output was the eigenfrequencies of the top. And we found out that actually the neural network could learn very well the way the structure vibrates. I'm gonna be with free time. I'm going too fast. So another thing we did, since we have a data set of 2,000 violins to train the network, actually we needed far less, but we anyway simulated these 2,000. It's to do a statistical analysis of the shape. In this case, in the right, you can see the frequency response, and I sorted the violin top plates by the mean frequency, which when you do PCA analysis of the eigenfrequencies, it's the best descriptor. And you can see that as the mean frequencies goes up, the shape of the violin grows. It becomes more elongated. And here is a data set that I'm varying the thickness, the shape, and the material parameters, so using different kinds of wood. This is quite important because the way of doing violins today, like here in Cremona, we live like in the cradle of violin making, where Stradivari was born. It's to copy the shape that the old master used to make. And the one problem that we have is that the wood is completely different. Wood from 300 years old, it's much drier, much stiffer, and it was grown in this 1500s. The climate has changed, the wood has changed, so you cannot use the same shape. And that's what this plot shows here. When you modify the material of a top plate, if you keep the same shape and thickness, the variation of the eigenfrequency is around 10%. If you optimize only the thickness and keep the outline constant, your error is still anyway big. But if you change the outline, and these variations are very millimetric, you can go to very, very low errors. And 7 minutes, perfect. And that's it. Thanks a lot for your attention.
Thank you. Okay, so do we have any question from the public? So don't hesitate to put the questions in the Q&A or raise your hands if you want to speak. So yes, we have one person to speak. Please, Jenpa.
Can you hear me?
Yes.
Okay, thank you. So I wanted to ask if, are you aware of anyone else using this same techniques for other instruments like guitar, for example?
Actually, before we wrote the paper, no, but I found a guy in Slovenia, if I'm not mistaken, who did it for guitars. But since it was like before like deep learning and all that, his paper didn't get any citation and he moved into doing something else. So I like to say we're the only ones doing AI and musical instruments.
Okay, thank you for the answer.
And we're also doing it for guitars, and we want to move into trumpet also, which are relatively close instruments to us.
Okay. So we have questions in the Q&A. So first, thank you for the interesting presentation. And he's asking, is there any specific reason why the neural network has been selected as the forecasting model instead of a more interpretable model, for example, random forest?
No, there is no reason. We just wanted to try that because there are a lot of examples of spin glasses and physical systems that work with this kind of network. So we took that. But it actually, if you do a linear regressor, it actually works quite well. And in the paper, we have some studies on the interpretability of the variables. We did a feature importance analysis, which tell us what are the most important variables in the chip. And those are the width of the violin and the size of the bows in the lower and the upper part. And the density and the stiffness, which is the sound speed of the material. So shape and material are the two most important variables.
Okay, thank you. So there is also a question from Elini, which is, who is asking, what if we will present humidity and temperature in a technical environment?
It's no, it's really that's such a pain in the neck because when we do experiments, we have to leave our wood in we have a castle here with a big bulb, which is temperature and humidity control, and we leave the stuff a month before we want to do any experiment. When the humidity and the environment changes, the wood will change, the way it will change, and everything changes. So it's, yeah, it's a can of worms.
So you would say that the climate change changed the wood for the best or for the worst? Like
the question is like global warming.
No, here it was just about the humidity, like representing humidity and temperature as a technical environment. But I'm asking, like, do you feel that the climate change change the wood for the best or the worst?
It's for the worst, because the higher it goes, the 0-degree isotherm, the less space you have for growing this kind of trees. And the hotter it gets, the faster they grow. So the quality of the wood is lower. So we're actually like going in a decline in the material supply for music.
Quality also, I guess. Okay, there is another question from Gianmarco. Okay, you can normally unmute. Yeah.
No, sorry, it was a mistake. Apologies.
No problem. Okay, so I have another question personally. So the size, what is exactly the size of the dataset that you had to use to train your neural network? Because you simulated quite a lot, but how much, I mean, how many data do you have to produce?
Actually, the eigenfrequencies are so simple that actually around 200 violins, you get it. But if you start to look the way the plates moves, it becomes much more complex, both in the terms of what network you need to use. Actually, we're going into like 3 hidden layers for describing the amplitude change, and around 500 to 1,000 violins. So
okay, so not that much, so that many.
Not that much, but that's comparable to a number of violins that Stradivarius, for example, made in his lifetime.
Amazing. So that's the aim, I guess, to have the perfect Stradivarius replication.
Or better.
Or better. Okay, so Johan is asking a question, but Johan, you can ask.
Jelena also has a question, I think.
Jelena, you had a question?
Yes. So I was wondering, do you have something which could be new to the violin producers, or something like, some simple message which your method could actually help violin producers to make better or cheaper violins?
Well, I think the last plot that shows that if you want to reproduce a violin, you need to change its shape. It's very important, and it's going to be very difficult to make luthiers understand that, because you also have the market, the classical musicians, they want to have instruments that look like a Stradivarius or a Guarneri's. So if you change the shape because the materials are different, people are not going to buy them. And that's, we will have to prove them that different shapes sound actually better than the old ones.
So there is a question from Julia. Is there a sound comparison somewhere one could listen to?
No. This is completely, COVID in between. These are purely virtual instruments. But we are starting in September another project where we are going to build the instruments, and we're going to CNC the top and the back, and then glue them by hand and try perceptual tests. So probably next year you will have news about that.
Nice. And so you're all luthier in your group, or just some of you, or subset of you?
No, I'm the only luthier in the group. So, but we're almost all like playing musical instruments. So
except violin.
Except violins, and except Fabio, who doesn't play anything.
And so last question from Naila. I am wondering how luthiers react to introducing technology into this craftsmanship that is artisanal, and if I can say sacred for many centuries.
They literally wrote a letter to the mayor to kind of stop our research.
Oh my God.
Because my boss is founded by the municipality, so they are so pissed off. It's incredible. I think they will come with torches and spikes to try to kill us if we continue doing this. But anyway, it's fun.
Okay.
Yeah, it's...
Okay, then good luck. Thank you very much for the presentation.
Thanks. I try to stop sharing this. Yeah.
So now I will leave the floor to Jelena to present our next speaker.
Okay, hello everybody. So our next speaker is Samir. And Samir and I are both coming from Serbia, and we both had this fortune in our life to spend a lot of our time in this amazing science center called Petnica, where we actually met. And when I say met, I remember Samir, but he probably doesn't remember me because I was a little student, and he was the one who was giving this awesome lecture, which I still remember to this day. And I especially remember one when he started with some blob of knocking, and then step by step, using different methods, came up with such a splendor of results that I'm still fascinated by that. And I guess this is the origin of his data-intensive astronomy approach. After that, he went to US and he spent time in many different institutions. He did his PhD in Ohio State University. He was in UCLA. And at the moment, he is a professor at Indiana University. And he came back to my radar last fall when Andrea Getz got the Nobel Prize in Physics. And among the papers which were quoted for her Nobel Prize, I saw the familiar name, Samir Salim, and I remembered his talks, and I thought it would be so awesome to have him here in DataBeers. So I contacted him, and here he is, and I'm very happy to have him. So please, Samir, go.
Thank you, Elena, for such an amazing introduction. I don't think I can live up to that hype that you put in there. And actually, unfortunately, I won't be talking about this work related to the Nobel Prize because that's been a long time ago. And since that time, I have moved on doing other stuff. So I'll be talking about other stuff that I have done so far. But you can ask me in the question anything about anything in astronomy, okay? So let me actually share my screen so that I don't forget to do that. Okay, so today I should be talking to you, about galaxies and about data because this is DataBeers. So in relation to that, we had these poll questions, and so the first one was, how do we actually get data in astronomy? Okay, and guess what? It's mostly just light. Okay, because whatever happens there in the universe, there's no direct way for us to figure out that. There could be sound waves propagating. Of course, gravity is happening there, but we can only infer about all of these things only by studying the light. Okay, so it seems like a big restriction. However, we can still find a lot. Now, alien signals, yes, that's why we're looking for aliens, because if we find aliens, they can tell us everything about the universe. Probably they know more than us. And then we don't have to spend all the money and the time doing that. But until that happens, we have to do it ourselves. Now, about the big data, well, yeah, I think you got it right here. We think that it has come a lot from astronomy, although certainly high energy physics has also been quite active in that respect, as you all know. But there's so many stars and galaxies, so it's got to be big data, right? Well, we try to, although we can also learn a lot from studying individual, like case studies, individual stars, individual galaxies. That's also valuable. So there are like two different approaches to doing things, and I'm more in the big data camp because that's what I think is useful for what I want to find out. Okay, so first, well, you heard about the Big Bang, the original universe, and it's actually funny how much we know about the first fraction of the second, the first minute, the first years. It's a very detailed knowledge, very precise knowledge nowadays. Similarly, when you think about the stars, how they evolve over their lifetimes and how they die, we also know a lot of details about these processes. We know how they leave the black holes behind, or neutron stars, white dwarfs. There's really very detailed knowledge about that. However, one thing that is still kind of not so clearly understood, it is galaxies. How they evolve over time, how they change since the Big Bang until now. So it's like 14 billion years of time during which they can change. In particular, one big question is, you see this galaxy on the left, it looks like a Milky Way, our own galaxy. It's creating a lot of stars. All these blue dots, they're young stars being formed in these spiral arms. However, we know that there are a lot of galaxies today that are not like that. They don't have young stars. they have no new stars being formed. They only have like this graveyard of old stars there. So there's this one big question is how and why this happens. And the reason why this is a very complicated question is because there's so many things going on with the galaxies, and they contain stars, they also contain gas. Actually, it's the gas that you need to be making stars. Where does this gas come from? It actually comes from what is known as the cosmic web. It's the space in between the galaxies. The gas comes onto the galaxies and makes stars. But, and that may be the reason why we don't see stars being formed nowadays in some of the galaxies, is it can be disrupted, this process. You can have collisions of galaxies that can destroy the disks in which the stars form, or they can even remove the gas from the galaxy. And furthermore, these supermassive black holes that sit in the centers of the galaxies, they actually may also disrupt this gas in the galaxy and actually make it so that it doesn't form stars. Now, to make progress in all of these and related questions, it's important to quantify things. We want to be able to measure things by numbers. So things like how many stars are being formed each year, like there's a time unit, rate of star formation. Second thing is the mass of the galaxy. It's not the same thing if you're looking at a small galaxy and a really big galaxy. They have different processes going on, obviously. So we should be comparing, apples to apples. We need to know that we're looking at the same kind of masses. And finally, there's dust. Okay, there's dust in galaxies, which it's also good to know how much of it is there, because it can obscure our view of the galaxy because of its absorbing the light. Okay. So also, we need to keep in mind that all of these studies are best done, in my opinion, with huge data sets. Currently, we have something like hundreds of thousands to 1 million galaxies in our samples, but very soon we'll be actually moving on towards more like a tens of millions of galaxies. So this is my approach that I have pioneered for this kind of studies, which is we use theory to predict how the galaxy should be, how much light it should be emitting at different wavelengths. And we use theory that combines different stars. We know, as I said, we know the stars very well. So we combine a bunch of different stars, different types of stars, different ages of stars, different amount of dust, put all of that in a model, and that makes us some prediction. Then what we want to do is want to compare this prediction with actual observations, okay? And that's how we can learn about what is the actual mass of the galaxy, what's its star formation rate, the amount of dust, because these things are known perfectly well in the model. We just need to see what observations actually compare well to them. Now, why do we need to use a big range of the electromagnetic spectrum? So it's not, when you say light, when I said in that poll question that we find out about things about the light, I meant light in a very general sense. Ultraviolet light, X-ray, it's also light, all sorts of electromagnetic radiation. So we are most familiar with the visible light, okay? And that is telling us mostly about different types of stars, including these older stars that have been around for a long time, which are more like a reddish in this galaxy that I'm showing here. And we typically get its observations from the ground, but also from space. You all know about the Hubble Space Telescope and its successor, James Webb Telescope. But if we move to the ultraviolet, which we can only get from space satellites, we can then see only and highlight the young stars. So the hot stars that are right now being born in a galaxy. So you see, it looks different when it's same galaxy when you switch to the ultraviolet. Similarly, if you go to the infrared, that's the emission of the dust. The dust is shining, quote unquote, in the infrared, and that's how we learn about the dust content of the galaxy. And also mention the X-rays, okay, because that's high energy, and that is typically associated with compact objects like neutron stars and black holes. So if there is this a black hole in the center of the galaxy that is producing a lot of energy and maybe messing up, how the galaxy is forming stars, we should be able to see that in X-rays. This galaxy actually does not have a very strong source there. And what you see here are typically just like normal black holes, not a supermassive one. Okay, so when we combine all of these observations and use the models to interpret that, I have been coming up with different results. And I want to highlight one thing that I thought is very, very cool. It's for a long time, this division between the galaxies that are forming stars and that have stopped doing that has been kind of like it's either or. However, these big data sets have actually revealed a sort of like a transitional category. Galaxies that are actually shutting down their star formation, they're on the decline, but they still have some leftovers there, okay? So we're sort of able now to capture this process happening in some of the galaxies, okay? And what is really interesting about them is that a huge fraction of these galaxies actually has these supermassive black holes inside of them that are actually spewing out this energy. So there may be a connection there, as some theorists have predicted. Now, the story is not over. There's still details to be understood about this process. And you also want to understand, when did this start happening in the past? And how long does it take for the galaxy to sort of transition into this more of a kind of a mode in which does no longer supports the formation of new stars? Thank you for your attention. And as I said, I'll be happy to answer any questions you may have about space, including aliens. Thank you.
Thank you, Samir. So now we can move to the questions. So please, anybody from the audience or speakers or organizers?
So there is a question from Isabella.
Yep.
Yes, hi, nice talk, everybody. I'm really enjoying this, especially I did a project in absorption spectrum of interstellar clouds as well, or target stars, so it's really nice to see. And also I had a question. It's more like, is there two questions actually. How much do we learn in a daily basis or in a yearly basis that we didn't know before in this scale of in a galaxy, in the understanding of galaxies? And the second part is there an issue with the sort of symmetry? So how do we really know, are we able to know if something is young or it's old? And are those two things similar?
Okay, so the first question is, what do you mean? You mean like, are things changing on a time scale of days in the universe, or is it just like the accumulation of knowledge in terms of our knowledge?
Accumulation of knowledge.
Accumulation of knowledge. Well, I should mention that there are like 80 papers every day being published on Archive, the online depository, and I would say that like anything else in the science, it takes time. It doesn't happen on the scales of that. I would say that scales of when we have like more radical shifts of knowledge, maybe on the decade, scale of the decade. So maybe a little bit slower than the 20th century nowadays, but we are still learning a lot. So like only recently we learned about some of the galaxies that may not have much dark matter, which is sort of pushing our theories in a different direction and things like that. So it is, I mean, our basic ideas are there, but so it takes time to really fill in these gaps, of course. So, and your second question is, I'm sorry, you said...
is it difficult? Is there some kind of symmetry between an early galaxy and a late galaxy? Is that difficult to distinguish?
Yes, so in terms of the age, and so we don't quite know, because we believe that all of the galaxies have started forming around the same time, okay? But the problem is the ones after that, some galaxies, as I mentioned, have stopped making new stars. So when you look at them, they're mostly containing very old stars in them, whereas others that are not. We are able to understand this on average. We cannot give a very detailed information about that because they're sort of lost in time. You know, the different fingerprints of the ages of all stars are erased, and we're doing best as we can. Of course, we can always look into the distance and see these galaxies as they were younger, and that is actually what we do a lot, pushing deeper and deeper. But we're also encountering that it's very hard to be seeing galaxies at such high distances. But that's, of course, the approach that you're using a lot.
Okay, nice. Thank you.
Thank you, Isabella. Thank you, Samir. So we have one question. I don't know if that's a question, but let's read it. It says, I didn't get much. That's Eleni. But what about the aliens?
Okay, so I don't know if Eleni can maybe expound on this question.
So Eleni, please raise your hand if you want to expand on this, and we are going to move to the other question. Since we are measuring objects in distance space, this is for Jacobo, is noise in the measurements a problem in modeling the evolution of galaxies? If so, how does the model account for noise?
Yes, absolutely. It is something that we must take into account, and we do that. And actually, that's one thing that I introduced in this technique is we do it Bayesian way. Okay, so we have created a gazillion of models, and we compare that with the data. And for each data point, like for example, the energy that is being emitted at that wavelength, we have the error bar of it. Okay, so when we do the comparison with for one galaxy in a gazillion models, each comparison creates one chi-square. And that gives you the probability that that model is the correct one. So it's E minus chi-square over 2 is the probability. So we actually build a probability distribution function for each of the parameters that we're interested in, for example, the mass of the galaxy, by taking into account the uncertainties in the measurements and even sometimes just the upper limits. So if something is not detected, but we know it's below that limit, we can also take that into this Bayesian fitting scheme. And that tells us in the end how well we actually have measured something. But yeah, that's a good question. Thank you.
Thank you. So Eleni raised her hand. So Charlotte, if you can let her talk so she can explain us her question.
Hi, can you hear me?
Yes.
Great presentation, great images, but I'm really sorry I don't get much of the content, but it sounds really fascinating. But I would like more to know maybe your opinion about all this alien thing that you mentioned in the very last part. Like, what do you believe about this? Like, it could be like an alien form of life?
Okay, that certainly is a very interesting question, and I think everybody has their own opinion. And the reason why we have opinions is because we don't have data. Okay, and what astrobiology is trying to understand is looking for places like planets where life could arise. We know that there must be. We already have found a lot of planets like Earth, so we know that the places like that life can exist. There certainly are plenty. Of course, I think, in my personal opinion, the biggest problem probably is biochemistry. Okay, that's not my field, but it's my impression that's very difficult to really sort of have some idea of how likely it is for life to form, because we don't really know how the life formed on Earth. And is it a fluke, or is it something that happens very frequently if the conditions are right? Life has formed on Earth, we think, kind of early in the history of Earth, which may speak favorably that it's common. But then again, we also know that the life may have formed only once on Earth, okay, or only one life form has actually survived, which then may speak against that being very common. So we just really don't know. It's one of the most unknown parameters is the likelihood of life. As for the evidence for any alien visitations, there's absolutely none credible evidence. I'll give you one example. We astronomers have cameras looking at the sky all the time, day and night, just inspecting what's on over the sky. There has never been anything really interesting found that would look definitely like artificial object. So I'm very skeptical about any alien visitations myself.
I'm not going to go to the UFOs, but a follow-up question maybe.
Yeah, you have another question?
Yes, you said that we don't have data indicating something like that. What would the data look like that would indicate an alien form of life?
So when it comes to just life, we are looking for biosignatures, which could come in the form of oxygen on Earth-like planets, which is typically the result of the biological processes. Also, ozone is also associated with life. Maybe also methane, although that can also be non-biological. And as for the intelligent life, pretty much what we can look for is our signals from space, which actually we have been looking for the last 60 years or more. So getting, like you just watch the movie Contact and see what I'm talking about. But again, despite a lot of searches, so far we haven't found anything. But the search is on. I mean, you never know. Next day, maybe that day.
Thank you very much.
Welcome.
Thank you. So one quick question for me to finish. So astronomy, people been looking at the sky from forever. And how did big data change astronomy?
Yes, so the big data changed astronomy, I think mostly because of the statistical power. So when we are limited to a small number of objects, it is very difficult. So like if it's in the hundreds, as it was for a long time, or thousands, and there's so many different things are potential processes are happening. And didn't even mention a lot of them, like the environment of a galaxy, the amount of gas, this or that. Then if you're trying to tease out different drivers of some phenomena, with a small sample, you really don't have any statistical power to do that. So that's essentially what is, I think, the most important thing, is that you build a strong statistical power. And the second thing is, you also get some rare objects that actually may be interesting. Obviously, when you cast a wide net, you're going to find some rare beasts. And sometimes those can be interesting because they lack some component or something really funny happened to them. They can be used as a test bed for certain theories. So that's I think, two ways in which this is really helping us.
Okay, we just got another question, so please a short answer to that. To study the evolution, does pairing galaxies with similar attributes, mass, gas composition, at different distances, as if it was the same at different point in the time works? Or is the evolution too chaotic?
So certainly, in order to be able to connect galaxies at the different distances and so on, we need to have some idea how they change over time. So some things we believe stay pretty much the same, whereas some others do change. So that's why it's actually a big challenge. It's that whenever we look at in the past, we are seeing universe when it's younger, and we see galaxies as they're younger, but connecting those into one story is very difficult. It's like you want to understand the development of a human, and the only thing you have are the pictures of kids in the kindergarten and then adults, but not the same people. So you don't really know which person became which other person, okay? So that is a challenge. We are trying to come up with different ways to connect that, but that indeed is why this is so complicated to do. So I wouldn't say it's a chaotic, okay, but there are still a lot of factors going on, as I mentioned, especially what happens with these more stochastic processes, like this active nuclei from the black holes kicking in. Who knows when that happens? Something, a cloud of gas may trigger it, and that can be just a stochastic event. So that does indeed make it more challenging.
Okay, thank you, Samir. One more applause for you. And I'm giving the word to Jose, who will introduce our last speaker for tonight.
Well, hello, everybody. So the last speaker of tonight is, again, because I like to bring my friends, someone that I really consider my friend. I met Isabella when I was still in Amsterdam. I was teaching a practical and she was one of the students, and she offered me arepas. That's all I needed. And then she told me that she was a DJ and started showing me some of her music. That was super, super cool. And I also found randomly a session that was being live in the Red Light radio, if I remember correctly. And well, later on, well, she has to send me a link with all the things that she had done. I knew some of them. For instance, she had been in the boiler room. I knew she was also in the school, and like recently in Bergam. She's actually my only chance to get in there, because the bouncer is gonna see I'm not cool enough to get in there. So like she needs to just push me in. But on top of that, she's also a PhD student in Berlin, and she's doing both computational and experimental work. And she's suffering her way through protein purification lately from the conversations we're having. And she has this very cool project that uses some of the info she learned in the masters that I was teaching there, and with her creativity, musical creativity, and she is going to make music with proteins, but I will let her explain it. The floor is yours, Isabella.
Thank you. What a nice introduction. Hi, Jose. Jose was my favorite teaching assistant, and I had a pleasure always seeing him in classes. And don't tell anybody that, but I already said it publicly. Anyways, so yeah, my name is Isabella and I'm a computer scientist originally, but I did bioinformatics and systems biology, and now I'm doing biophysics to understand the progressive and aggressive nature of neurodegenerative diseases by making models in vitro and in vivo, and more on the biophysics level. So we want to understand the dynamics of disordered proteins. But then let's skip all of that. And today we're going to talk more about amino acids. So from the questions I have said, people seem to know what are Sine-Phi angles, and I will go into it in detail in my talk. And so the Sine-Phi angles, in fact, are the measurements of the torsion between the alpha carbon. This is a normal vector, and I will refer to this again. The magnitude is the measurement between these two atoms. And the Sine-Phi angle is the freedom, when the torsion of the normal vectors between the amino acid residues. So if I was to, this is my alpha carbon, the torsion is this angle and this angle. And for the second question I have, most people say yes, but they don't know what to do. Well, that's a difficult question, but I think that there's a place in the world for everyone to share their work and their art. And all it takes to tell somebody that you've done something. Like today, for example, I've told Jose I've done this, and that's why I'm here. So feel free, just talk about it to your friends, build a network, show your work, don't be afraid to do so. There's definitely room for everyone in this world, specifically in the art world, even though it's a bit scary. But I can tell you from experience that it takes time, but it is definitely possible to make a career in both art and science. So I will share my screen. Okay. So I will be presenting Potein Synth today, which is a script I made that reads the code from amino acid sequences and actually the three-dimensional structure of proteins. More specifically, I will be looking at the spike protein in the COVID-19, and we have found the sequence and of course the structure of this, and that is essentially my input data. I will be a bit technical, so feel free to ask me questions at the end. So I'll be happy to repeat and clarify them. So we have 21 amino acids. They have different types, different aspects to them that make them behave in certain ways. For example, some of them really like water, the side chain of them like water, some of them don't like water, some of them like both water and not. And these make these amino acids behave in certain ways. So sometimes when they don't like water, they like to crumple up. And when they love water, they like to swim around. So this is the three-dimensional structure of amino acids, and they basically are in a chain. So a protein is a chain of amino acids, and the intermolecular forces allow for the secondary structure. And I'm going way too fast. I've never presented after having 2 drinks, by the way. So to get a little bit more technical, we have a sequence which comes from DNA. So from DNA to RNA to amino acids to protein. The primary structure is basically just the order of these amino acids in a chain. The secondary structure is typically alpha helical or a beta sheet, which look like these little spirals or these sort of long pleated beta sheets. Tertiary structure is when they fold, when a protein folds and has a shape. And quaternary structure is when the different proteins come together and form a complex. We will be focusing mostly on alpha helical structures, and this is actually a pi mole model of the amino acid chains together in an alpha helical shape in the spiral from the top as well. And beta sheets, you can see the chain going actually in this direction. So that's a parallel beta sheet, and that's an anti-parallel beta sheet, and this is the three-dimensional view from the top. So the interesting thing is that in nature, these alpha carbons actually have sort of the tendency to cluster in a certain way. So these psi and phi angles I mentioned earlier, they seem to always appear because there is some constraint. The constraints are made by the van der Waals forces. So if you see there are some constraints of the chains that create these the psi and phi angles. And when you simply just plot the phi and the psi, you can find clusters of when the protein or the secondary structure will be a beta sheet and when it would be an alpha helix. And this is interesting because this is just a pattern that we have in nature that was discovered by Ramachandran. So the way that we get these data, or the data I will be presenting, is there's several actually, but we can put a protein or a molecule into a crystal structure, which actually first is a liquid and then it's a crystal. You can shoot X-rays, and then from the projections of the diffraction with X-ray, you can have an electron density map as well as a protein model, which again, it focuses mainly on the alpha helical and the beta sheets. These models are actually, you can download them from a site called Protein Data Bank, where most of the scientific community uploads their findings. And the data just looks like an atom, the type of atom it is, and Cartesian coordinates of the atoms in 3 dimensions. So I will be looking at the Cartesian coordinates of the cryo-EM structure of the spike protein, which basically is just a frozen molecule where they do atomistic level accuracy with electron microscopy. And to go into the musical side, the scale will correspond to the likelihood that the amino acids will not be on the surface, or if it will be on the surface. So basically, if it likes water or if it doesn't like water. So again, the scale is the propensity to be varied. Magnitude is the length between the alpha carbon and the other carbon at the other end of the normal vectors that I have shown you at the beginning. And the psi and phi are the velocity of when the key is pressed. So I will very quickly show a demo of the script. Here we translated directly from the amino acid of the spike protein. This program is called Ableton. You can play around with a lot of parameters and make really nice sounds. I can go ahead and answer some questions and lower the volume if you want to continue hearing. Thank you.
Okay, thank you very much, Isabella. So we're open for questions. Actually, I can see some comments. Nice. Okay, Jelena has one.
The music sounded very nice. My first question is can you give us the whole thing so we can put it on our YouTube channel? I think it would be nice to have the whole piece.
Sure.
But what do you do you think that this could be used as visualization of the data, which can actually tell us something more about it?
Yes, I think so. I mean, the interpretability of data is key. And in 3 dimensions, it's quite difficult to imagine anything other than a visual. Even the visual spectrum in 3 dimensions is quite difficult. One idea I had was to follow the trajectory of the amino acid chain and have the left and the right audio to signify a change in your direction. And that was another project I wanted to work on, as well as basically just translating any data to a different point of view. It will probably give us more information, or even just like we do it all the time. We reduce the dimensions of things. So why not translate into auditory? Yeah.
Do you think this music would sound different if you just took a random generator, or?
Well, that's a good question. I mean, so of course, I mean, we can argue that this is a random generator as well. But is it so random?
Thank you. There is a question from Ramji and Jose, you also?
Ramji first, I think. We don't hear you, Ramji.
Yeah, sorry. Yeah. Well, I unraised my hand. I forgot to unmute myself. My question is, it extends on Yelena's question, sort of, but the other way around. Did you have to choose the scale so when in such a way that the interpretation would sound more musical to people accustomed to listening to music of a certain tradition?
Yeah, you definitely. I chose one that was called Hawaiian tuning. So basically, the code looks like you can assign any note to any amino acid. But what I had done originally is assign it in linearly, so it did not sound very musical. But then the scaling was determined with the propensity to be buried. So the order in which the lower notes and the higher notes, they had some logic. They had a probability distribution of the way it behaves, if it crumples in the center or if it goes to the outside. So this was the scale. Yeah, I mean, with the script, which actually I plan to share on GitHub and make it available for everyone. It's actually from my school. I used the script from my school with Jose. And all I did was translate the information we got from these psi phi angles, because we tried to predict the secondary structure. So yeah, you can add any kind of tuning to it.
Yes, so we have 2 questions on top of mine, but a bit later. First is Mateus saying, as someone from a completely unrelated area, but not tone deaf, I could notice that there's a certain rhythm to the sound. Is there an explanation to it?
Yes, so the length of the note was the magnitude. So basically, the magnitude between the amino acid, the carbon atoms.
Okay, can you explain maybe a bit more for people that don't know about amino acids, what the magnitude is, like the distance of what it is?
Yeah, so the magnitude is basically the length or the distance between these 2 atoms. So if they were, depending on the torsion, they would change the distance.
Cool. And then we have another question from Eleni. It is really amazing. Thank you. I saw you have done some work in visual arts. Could those 2 be combined?
Oh, so yeah, I would really like to combine them. I haven't done that, but as maybe didn't share before, the reason why I made this was because somebody told me you should combine art and science, music and science, and I thought I have no idea how to do that. And then I was offered to do that at ESTEC, the European Space Agency, which led to the absorption spectrum internship, in fact. And it was just by chance that someone said, oh, you should try to do that. Yeah, maybe someone should ask me to try to do it, and then I would combine it officially. But no, I never have. when I did my studies in filmmaking, I did score films, but I haven't never done audiovisual in any other way, or at least not with while performing music.
So I'm gonna go now. I see that Johan has one, but I don't want to skip my question either. So you go later. I was wondering, now you have taken protein and have converted into music. Now I was wondering, would you make music that then you will convert into a protein? Would that be a challenge, composing something that when you make it to a protein, it actually makes sense?
Well, if you use the same scaling, yeah, of course. I get. Well, we can see, we can make the initial structure, just the sequence, and see use AlphaFold and see what it produces.
Nice. I think Johan, you go now.
Yes, thank you. So actually, I think because your question was, is this music a representation or a audialization? And I wondered, so there's clearly a very strong preference to visualization to explain phenomena in science. So do you think it introduces bias in our judgments? We draw conclusions based on visualizations all the time, on graphs, and in the end, it's typically 2 lines and they should be close to each other and so on. So could we get my question then is, could we get a new perspective by considering audializations?
I think you would get definitely another perspective from audio. It really depends. I mean, if you are looking at big data or lots of features and you want to do feature reduction, of course you lose, you are very biased. And in fact, that bias is necessary for prediction. So we know that, but the question is, in 3D, if something is in 3D and it's represented in 3D, it does not lose information. So I think that sound would add another perspective, yes.
Yeah, so maybe we need journals that add sound to their, like typically, if you write a paper, you have a graph, but maybe we need, and we have internet and all computers, maybe we need a sound section.
I would listen to nature podcast sounds. That would be awesome.
Thank you.
Nature beats. I feel like instead of lofi, right?
But actually, going back to an earlier question about how life was formed in the biochemistry, the perspective there. This is what I learned from another biochemist, because clearly I'm not a biochemist, but I am doing biochemistry now. So the theory is that the water from the ocean goes up and down the shore, and there's sand, and there's water trapped. And from the heat, the water trapped there's a number of molecules there. And this is essentially how life is formed. Another theory, or the paper that was published a while ago, was if you take everything that is on Earth and you ionize it, you get amino acids, which is what I've been talking about today. And then a portion of my paper with the fullerenes that occur spontaneously in space, or basically these carbon spheres that might trap some small molecules inside. And they exist in clouds because they happen from combustion. So there's a theory that comets come and they may collide with them, or in fact, there are meteorites that have about 80 amino acids, 8 of which are proteomic, and they found them in Antarctica. So we're not sure exactly where life begins, but we know that what makes life already has existed, or it exists. And additionally, there's the phosphine that was detected in.
Let's not go there.
Why not?
This has been retracted almost because of
okay. I wasn't
the data. It's actually appropriate data issues. Yes. data calibration issues, things like that. So it looks like it's actually, unfortunately, it seems like it's going to go away.
Oh, okay. I didn't know. I wasn't sure about that.
Yeah, it was sort of, yeah. But
well, that's too bad.
The ingredients for life are plentiful in the universe. The ingredients for life. Now, getting the metabolism to actually function and the code to code the elements needed to do the metabolism, well, that's the big challenge, I think, right?
Yeah, it takes time.
Yes. So we have two more questions that I haven't seen from the public. We have Philip. I think Charlotte can allow you to speak.
Yeah. Can you hear me?
Yes.
Okay, cool. Hi, great talk. I was thinking it would be interesting to use this method somehow to help with protein folding. So when you kind of need to, well, proteins kind of fold in quite complex shapes, as you kind of showed, but it would be interesting to kind of, the more they get to their final form, the more harmonious the music would sound. So you would start with kind of a weird cacophony, and then towards the end, when it kind of folds up into its correct shape, you could then say, okay, yes, this is a harmonious melody or something like that.
It's a good idea to make the sounds of the progression of an unfolded protein to a folded protein. But actually, the data I used is used precisely to predict protein folding. AlphaFold is training on the PDB files. And by nature, just as I said, we just plot these angles, these dihedral angles, and we can predict secondary structure, these alpha helical and these beta sheets. So yes, in fact, this is exactly what is being used for predicting the structure of a protein. Not my code, but the data. Although, yeah, actually my code, yes, but only secondary structure.
Yeah, okay, got it.
Yes.
So you could add kind of like a third dimension by making like an orchestra.
Yeah, I mean, that would be more neural network, perhaps. I believe they used a transformer. I'm still not, I don't know if they have published the paper yet. Okay. But yeah, they've used the torsion angle and the sequence to do their first version of AlphaFold. Maybe, are you familiar, or I'm not sure if you are?
No, I'm not. I just know that protein folding, predicting correct folding of proteins can be quite challenging.
DeepMind, Google's DeepMind claims to have solved this 50-year-old problem, but they don't claim that, in fact, 30 to 50% of the genome is disordered. And so you cannot actually predict a structure from it. So DeepMind, you should check them out. They've done a lot of work on that. But my PhD is on understanding the behavior of disordered proteins. So we don't really know what shape they will take depending on what they do. So yeah.
Thanks. Very cool project.
Thank you, Philip. So we had another question, but I think it has been already answered with the whole AlphaFold discussion. So I think Johan still is raising the hand, but he has already asked everything he wanted to ask, right?
Oh, it's okay.
Okay. No, I think it's just yeah. So okay, I'm going to give the word now to, I think it was Yelena that wanted to say something. So.
Yes, we have the last order of business for tonight, and that is like who is going to get the beers. So, our executive committee of Ramji and me decided for the following one. So, okay, Ramji, if I make mistake, you have to correct me. So, Eleni, Naila, Isabella, so one of the speakers is also getting a beers. Jacobo, which I think has collection from us already because he gets one every event. And finally, Mateus. So I don't know if you all are geographically close enough for us to send a beer. We can send to Belgium and definitely some neighboring countries like Netherlands and France. And Jose will look into it and see how far we can send. You should be registered, so we will send you an email asking for your address. If you don't get an email for us, please write to us, because that means we kind of can't find you, okay? So we do want to send you beer. We are not ignoring you, so just please send us an email, okay? Our email is databeersbrussels@gmail.com. It's very easy. So yeah, do you want me to close, Jose, or you want to close?
Well, I'll close myself. It's fine. So thank you very much, everybody, for joining. It's been lovely. Let's see if the next event can happen live and we can actually enjoy beers. And it's an important part of the whole DataBeers experience. And yes, have a good Thursday, everybody, and see you next time.
Thank you, Jose.
Thank you.
Thank you, everybody.
Bye.
Bye.